Yeah, so in the last class, probably during the stream, I spoke about a particular problem, okay? In the stream, I discussed about two types of concepts, okay? One of the concept is the large signal behavior, looking at the node Vout as well as the node Vx, okay? With respect to the variation in my Vin. Just because the Vb is trying to define the drain potential of my M2 as well as trying to define the drain potential of my M1, I cannot increase the value of Vb larger or I cannot reduce the value of Vb smaller, okay? So the reason is all been done in the stream. You please just go through it, okay? Yeah, so there is a kind of potential Vb that stucks between the drain of my M2 and stucks across the value of drain of M1, okay? So it cannot have a liberty to just sweep around a range of value in it. The Vb suffers. It has only a specific range of value and it has to be carefully chosen such that I end up having a large amount of swing both at the node Vx as well as at the node Vout, okay? So if you fail to provide an appropriate value for the Vb, then the circuit will have a limited swing either across your node Vx or across your node Vout, okay? So that is the major drawback that we have just because the Vb is stuck between the drain potentials of M1 and M2, okay? So, and also there is also one more drawback that I stated when I try to address a particular problem in part B of Cascode Amplifier. So what I said is that what is the gain of this particular circuit first of all? How will I derive the gain? What is my capital GM? I said some approximation. Yeah. So whenever I try to compute the capital GM, I assume that the lambda is equal to 0. Okay. So with that approximation, I could write that the value of this capital GM is nothing but my GM under itself. Okay. Now, what about the R out that I have? Yeah. So it is just RD in parallel with the Rx. Okay. So by now you know what is the value of Rx, so I will not repeat it. So I have this Rx which is very large compared to the value of RD. Now that when I try to multiply with this minus GM1, will I get a large gain? Yeah, so why is that I will not have a very large gain even though, yeah, so the RD value is small. That when I put it in parallel with a very huge resistance, effectively I will get a very small resistance, right? So now because of the small resistance, what is happening is even though I have started two transistors, I'm not getting much gain out of the circuit, okay? I still having a gain that is almost closer to the value of CS amplifier. And also I'm trying to lose a VOV out of the output swing that I have here. Okay. When I compare this cascode with respect to my CS amplifier, I'm not getting high gain. The other thing is that I'm also losing my VO minimum has currently has to satisfy these voltages across it. Okay. So these were the disadvantages I have. Now let us try to rectify one of the disadvantages that I have stated right now. How I can increase this gain? Is there any way by which I can increase the gain of the circuit? What about increasing the value of RD? Yeah, that could increase the value of R out. In turn, it can increase the value of gain. But the whole point is that when I use a resistor, it occupies a large space in my chip. I don't want to do that. Is there any other way I can do it? I can use a mass. Yeah, so we know that when I take a mass transistor, basically the current has to flow, okay? So we also know what are the impedances that I see when I look across each of these points, right? So when I look across the gate, it is infinity. When I look across this, it is 1 by GM, approximated value. When I look across the drain, it is R naught, okay? Now, which point could be fixed in order to have a very high gain? And also make sure that the currents are flowing through the device, through the terminals that you are choosing. So the whole point is that if I could be able to replace this resistance with this device, will I get a high impedance? So now what is the value of resistance that I have when I look up? It is R naught, okay? So again, when I try to plug in here, this R naught sits in parallel with a very large resistance just because this quantity could be approximately written as GM2, RO2, RO1. So again, this Rx is a very large value compared to the value of RO1 or M3 I will write it, so RO3. Is that clear? So again, I'm not getting a better gain out of the circuit. So what I can do? So what happens if I try to stack one more transistor on top of it? It increases, right? So whatever transistor I have to plug in, it's a PMOS. Now which terminal I need to place it on the source of this M3? Drain or source? Drain, okay? Yeah. So what I can do is that I can just take off this node and then try to add one more transistor at the top that would actually give us this M4. And now when I look across this M3 drain, what is the resistance that I see? Yeah, so basically I have a resistance whose value is RO4. That when I look through the drain of this M3, what happens to this RO4? It basically gets amplified by the intrinsic gain of this M3 transistor, right? So now in the place of this RO3, which was previously quite small, right now the value has got raised up to a very large value. So again I write it as GM3, RO3, RO4. So again I'm writing only the approximated value here, so you know the remaining part of the expression, so I'll leave that to you. Okay, so this is how I can do it. But is there any drawback in this particular circuit when I try to increase the gain? What is getting reduced? No, GM remains same. Yeah, V out. What about the swing that I would get out of the circuit? Yeah, so whenever there is a swing, let me just pull out this particular structure. Yeah, so whenever there is a swing across a Q point, okay, now whenever I go up, I have to make sure that I leave a minimum voltage drop across my drain and source of M3 and drain and source of my M4. What is that minimum drop that I have to maintain such that both of M3 and M4 remains in saturation, VOV. So if this is my VDD, I have to have a drop of VOV4 across this VDS4 and VOV3 across my VDS3, okay? And when I step down, again, I have to maintain a minimum drop across this transistor M2, which is nothing but my VOV2, plus the minimum voltage across my drain and source of M1, which is supposed to be VOV1. Is that clear? So in the previous case, we had a VO maximum that was reaching almost close to the value of VDD. But now, in order to improve the gain, when I start adding the transistors, the upper swing has been limited by, what is the maximum value I will get over here? VDD minus these drops, okay? And that is the maximum value I can get out of the circuit. Is that making sense? Clear? Yeah. Now, say for example, if you want to further increase the gain, what I can do for it? Yeah? You can just think. So however we did, right? Why can't you think in the same direction? What happens if I put one more transistor, stacking one more transistor, both across my PMOS structure as well as across my NMOS structure? What happens to the R out? It boosts up very large, okay? So you know how to compute that. If at all, if I have 3 transistors stacked one upon each other like this, you should be in a position to know what is that impedance is. How would we compute that? Say for example, I have bottom transistor M1, M2 and M3. What is the value of Rx that I would get out of this circuit? How to compute that? Okay, step number 1 is to find what is this impedance first, right? And a further step down is to know what is this impedance first of all. Okay, yeah, so what I have here is an RO1, and that when I pass it through this M2, then I can get this value. And this value is nothing but GM2, RO2, RO1. And this entire impedance, I can model it as a kind of resistor being attached to the source of my M3. Okay, this value is what I have plugged here. Now when I look through this M3, what happens to this resistance? That gets further magnified by the intrinsic gain of this M3. So it's as simple as that. Okay, so that I can shoot up this R out. Clear? But you always have to be cautioned that whenever I stack the number of transistors higher and higher, what I be losing? The output swing would be reduced. Okay, so be clear with that. I'll just state whatever I said at the beginning. That is, now because of this restriction, I have to carefully choose my VB value. Even if you choose carefully, somewhere I'll be losing this swing. Okay, so now is there any way by which I can get rid of this issue? What is the relation that I have between the gate of this M2 and the drain of this M2? In order to stay in the saturation regime, I have to make sure that the VB minus VT is less than or greater than with respect to VD. Yeah, it's supposed to be less than or equal to my V out or VD2. Okay, so this is nothing but my V out. Now this is a constraint that I pose on the value of VB, looking from the drain of my M2. But what is the constraint that it poses from the drain of this M1? We know that the value of VB is nothing but drop across the M1 VGS or M2 VGS2 and VDS1. Okay. Now, how does this VD1 defines a constraint? Can I choose a value which is small, or what is the minimum value that I can choose for this VB, such that my M1 stays in the saturation regime? Yeah. So for a defined current, this value is fixed. Okay, so there is no modification for the value of VGS2. But what is the minimum value I have to maintain across this VDS1 such that my M1 stays in the saturation regime? VOE1, right? You see, as I said before, the VB is restricted between the drain of my M2 as well as the drain of this M1. Okay, so I just want to break this. I have this sort of issue. Okay, I cannot neither go down, neither I cannot go up, just because of this restriction. I've been stuck between those two values of drains. Can I think about a circuit or a device that can handle a drain potential that is smaller than the value of VG? PMOS, how do I write for a PMOS device the edge of saturation condition? For a PMOS device, the entire relation of VGS minus VT, okay, so that is what I try to say. So if at all, if I have VGS minus VT, in order to stay in the saturation regime, I can have this condition. Okay. Now in this case, you could able to see my source potentials can be left over. Just because the source is common to both, I can just write it as VG and VD. Okay. So that is what I have done on the top expression. So now in this case, I can have a gate potential or the value of VB large enough than compared to the value of the drain. Okay, does it make sense? So in the previous case, the drain was making my gate potential to be always smaller, okay, for the M2 transistor. But now when I try to replace this M2 with a PMOS, then it poses a different direction. It says that my gate has to be always higher than the value of drain in order to stay in the saturation regime. The moment I invert one of the transistor from NMOS to PMOS. Okay. So now, how would we build it? I got an idea, but I need a circuit out of it, right? So how do we do that? Did you really understand the main problem with the Cascode amplifier? So I have a value of VB that cannot go up just because this guy is hitting me. I cannot step down just because the VDS is defining me a minimum value here. So it's been stuck between both these people. Now, I want a particular circuit that helps me either to move this VB higher or move this value of VB lower. Okay, so one way I can think is by looking at a different device, which is a PMOS. Okay, that tells me that I can have a value of VG that can be greater than the value of VD plus VT. Okay, that is what I use as my idea. But how will I build a circuit out of it such that the VB has some sort of liberty to move in one of the directions? Yeah, so one of the transistors, if I could able to replace, then everything could be done. Now, as you said, I could replace M2 with a PMOS, but I will begin with M1 replacing with PMOS. Okay, I'll retain the value of the transistor of M2 as it is as an NMOS. Okay. Now, that type of configuration we call it as a folded cascode. Okay. So we call this structure as folded cascode, and again there is a further refinement for this name. I'll just write it. So what I've done here is that I took the drain resistance RD, I retained the value of M2 as it is as my NMOS, but rather than connecting an NMOS towards the source of my M2, what I've done is that I'm trying to connect the PMOS. Okay, so which terminal I have to fix here? If I put a source, the output impedance will be a different, right? So because the impedance that I see, I still want to maintain it as RO itself. I don't want to put a source over there and reduce that impedance further. I have to go with drain only. Okay, so yeah, you're right. Right. I thought I will ask that question. Okay, so the only thing is that I just invert this particular M1 from NMOS to a PMOS. But the point is that, can I connect the source to the ground? No, because a PMOS device should always have its source terminal to a higher potential than compared to the drain. Okay, so what I do is that I just draw this and put it towards VDD. Okay, or in short, I just draw the circuit in a completely different way. I have the source and the drain is connected here. Okay, and this is my M1 and this is my M2, and here is where I feed my input signal. Let me just ask, is the circuit is properly been biased? No. Why? Is there any potential difference from this point to this point? No. Then no DC current can flow, right? You need VDD to ground to have some sort of current to flow, a DC current to flow. So how will I make the circuit biased, first of all? Any idea? I want the circuit to be functional. So now no DC current flows, and this circuit is absolutely useless because none of the transistors are in saturation region. Okay, I will not make you to think too much. I'll just put a tail current. Okay, I just add a tail current. Now, I have IS, and the value of this IS comes from two transistors, right? The DC current that flows here is basically a summation of current that flows from M1, also a current that flows through my M2. Okay, because there is a potential difference right from this VDD to ground. Again, there is a potential difference from this VDD towards ground. So I have current in both the parts, and they both add up to create this IS. That is clear? Now this circuit is properly biased just because the currents are flowing. Clear? Now let us look for our answers, because that is more important for us. So what I do is that I'll just look for the small signal. Let us try to address this capital GM first, and then we'll talk about the swings. Now what is this value of this capital GM for this circuit? Will it be GM1 itself? When I talk about small signal, what happens to this tail current? Open circuit, so nothing to worry about this IS. Now, when I talk about, so this cascode amplifier, how did I approximate the value of GM? The small current that flows here, when you tap this node to the output, to the ground, I get an output current. And this current is the same current that I drive through this value of Vin. So whatever I had it as ID1, which is GM1 times that of Vin, was being taken out as I out, which is an approximated value. Based on that, we computed that the value of GM, which is I out by Vin, as minus GM1. Can I use the same rule for the circuit? So what happens to these nodes when I try to translate them to a small signal? This goes to the ground. I have the small signal Vin, and there is a potential difference between the gate and the source, due to which there is a current that exerts across my M1. And that current value is nothing but the same ID1. Okay? And the value of this could be returned as, I will write it as minus GM1 times that of Vn. Don't ask me why I have written the negative sign, just because I put the current direction here, something which flows from source to drain, even though I have polarity as plus and minus here. Okay? Or if you want, I'll just replace that, okay, if it confuses you. So I have plus and minus, and due to which the current always flows from drain towards the source. This is what I have as a current, small signal current. And this current should flow out of this circuit as I out, right? So it flows in the opposite direction, due to which my I out is returned as minus ID1, which is nothing but minus GM1 times that of Vin. So I out by Vn will get us the same value of GM1 itself. Okay, this is again an approximated result. I have not encountered all those R0 and other things here. Does it make sense? This current that I am looking is basically the current that is flowing here. Yeah, sorry, I forgot about one important names for these transistors. So I'll just quickly do it. So what do we call this M1 as? There is a special name for this M1. When we spoke about a CS amplifier with current source load, okay, we had a special name for this M1 and M2. What are those names? This is VB. So this M1 was called as input device, and we call this M2 as not output device but load. Okay, so that is what we said. So whereas in this case I have not just 2 transistors but more than 2, right? It's almost like 4 transistors I have. So each of these transistors have a name for it. So let me begin with this M1. So what is this M1 is called as? It's again input device because I'm feeding my input to this M1 transistor, so I call that as input device. What about this device? This device is called as a cascode for the input device, okay, because it has been stacked on top of it. So I call this M2 as a cascode device for input device, okay. Now again, what do we call this M4 as? It's a load, okay. So this is called as a load. Then can you guess what is the name of this M3? Yeah, it's a cascode for the load, okay. So we call this M3 as a cascode device for the load and M2 as a cascode device for the input, okay. So these are just the naming conventions, clear? Yeah, so nothing to worry. In case if they specify that the cascode dimensions, you should be in a position like which particular cascode we are talking about. Whether I am talking about M2 or M3, it will be clearly mentioned in the question, okay. So if they are stating that the cascode device for the load is 100 as the aspect ratio, then you have to take this M3 as its W/L factor, clear? So please make sure that you are comfortable with these namings, clear? Now, had we really addressed the issue of moving this value of VB? That is the next question, because the whole point that we went from cascode device to folded cascode is that the VB was being stuck between the value of VD2 and VD1. I was being stuck in between. Now, with this circuit, can I make this VB to go higher than the value of VD2? No. No or yes? No, right? Because it's an NMOS device, okay? So I have to have my gate potential or VOV of VG minus VD supposed to be smaller than the value of VD, okay? But can I bring the value of VB down? Yes. Why? Because as I reduce the value of this VB, what happens is that I'm trying to push the source node towards the ground, okay? Now when I do so, the drain of this M1 is going towards the lower potential. Now will my transistor stay in the saturation regime when I try to do so? Now why is the source potential has to go down when I try to vary the value of a gate potential? We'll think about the source follower. What is the literal meaning of source follower? Whatever the gate input is, the source has to follow it. That's it, right? So when I reduce the value of the gate input, obviously the source node has to push that particular source potential in the same direction, okay? And the reason is in order to maintain the current. Yeah. So now this has actually made comfortable that I can reduce the value of VB to small values, okay? But VB cannot higher, okay? So it cannot go high. Can you think about a circuit where I want this VB to have a larger value than compared to the drain? How would you draw the circuit of it? Can we think about it? In this case, so I have VB that can go down, okay? There is no restriction from my drain of M1. Is there any possibility way of pushing my VB value more than the drain of M2? How will I have a circuit like that? Yeah, can you do it? Can we have a try? And later we'll talk about the namings for those two structures. But I just want you people to make a try. Yeah, so if I replace this particular M1 with an NMOS and replace this M2 with a PMOS, then for NMOS, where's supposed to be the source terminal, source potential? Towards the ground. So obviously this transistor will be placed here, just because the source of an NMOS will be the lowest potential. So this will flip. What about this guy? When this flips, this will also flip down. So that, yeah, the better way to think is just by looking at this M1 itself. So we know that the M1 have this Vin, and right now it is an NMOS, so I just put it down, and that has to connect to the source potential of my M2 transistor. Just see, the drain of this M1 is connected to the source potential of my M2, but right now the M2 is a PMOS device. It has to be at a higher potential than compared to the drain. So due to which I start with this, I think the current is, okay, source of M2, and the drain is here. You see, the drain is smaller compared to the value of this source potential. Clear? And then there is a resistance, because if at all, if I want to read out a voltage, I have to pass that current to flow across a load, okay, to tap my output. So I just pass it through my load, RD, and take here as my Vout. So in order to make this working circuit, I have to still add a tail current. So in this case, it is not a tail current, head current, okay. So the mirroring is supposed to happen something like this, and the gate of this is connected to VB. Let us try to move this VB potential lower than the value of this Vout. Is there any restriction? Can I move this VB potential to be smaller than the value of drain just because it's a PMOS device? For a PMOS device, we know that the VG minus VT is supposed to be greater than the VD, okay? So with that condition, if I try to push it down, what is happening is that my gate potential is stepping down, and that would make this M2 to get into linear regime, okay? So I cannot push it down. Now let us see whether I can push this VB potential higher. When I try to push it higher, what is happening is that it's a source follower, due to which this potential is also rising. It's a source follower for my M2 transistor. So whatever the gate that I have, the same voltage is being followed by the source. So due to which the drain is also being pushed up. Is my circuit M1 stays in the saturation regime when I try to push up? Yes, okay. So in this case, the VB can go higher, but cannot go smaller or something. Yeah. So now, as I said before, there's a special name for this circuit and for this circuit. So we call this particular circuit as folded up configuration. And for the folded up configuration, the input device is a PMOS. Is that clear? And the configuration that I've drawn here is known as folded down, okay? So for this folded down configuration, we have an input device which is an NMOS. Okay. So now that we just somehow got rid of this restriction that was posed on the value of VB. Now there is also an important task that has to be performed to know what is the output swing that I have. Am I right? So we'll try to address this with a large signal analysis, and we'll get to a very beautiful point out of this analysis, okay? Let me take this particular circuit which is drawn here. So now what I do is that I'll just try to vary my input voltage which is fed to the gate potential of my M1, and try to see how does this current through the device behaves and what is the corresponding output I'm getting out of the circuit. Clear? So we'll begin with this currents. Now what happens when the value of Vin is equal to 0? So Vin is a potential that reads between this gate and the ground. Okay, so right now there is no potential difference. Is my transistor M1 is on? Why no? The source is at VDD, gate is at 0. So I have a large value, the value is almost equal to VDD. The VGS value of my PMOS is very large. Okay, so in that case my transistor M1 will be on, right? Now it's a very large value, which means that all of the current that has to flow through this tail current source has to flow only through this particular path. Am I right? Because I have a very large value here and no current can flow through this particular path. So in a sense, all of the current right now that flows through this M1 would be equal to IS itself. Clear? Since because it gives me a large value of VGS for this input condition. So let me mark a green color for this input device, and that is equal to IS. Now what about the current that flows through my M2 transistor under this condition? It's supposed to be equal to? Now when all of the currents are being flowing through this particular path, what current can flow here? 0, right? Because IS is nothing but it's a summation of ID1 plus ID2. Now in this case, if I say that the value of ID1 is equal to IS, means that the ID2 is supposed to be equal to 0. Only then I can have this equation valid. Am I right? So since because all of the currents are flowing through this ID1, the ID1 is currently having a value which is equal to IS, but the current that is flowing through my ID2 is basically 0. Okay, so I'll also mark this particular point, which is ID2 here, which is 0. Now there is a particular value of Vin. Let me label that Vin to be equal to Vin1. Okay, because it's a value which is starting from 0 and I'm just had enough value of Vn. Okay, so currently the value of this would then be read as, the VGS2 is read as Vn1 minus VDD, or if you want to swap you can just do it. Okay, yeah, so under this condition what happens is that the current through this M1 device has got dropped, but the tail current is expecting the same current of IS. Okay, so if the current through this device is getting dropped just because I've raised the value of this Vn, where is the remaining part of the current has to come from, to the tail current source? Are you clear with this? Shall I go with the numbers in order to demonstrate this? Okay, let us assume that my IS is expecting a current of 1 milliampere. Okay, for when the value of this Vn is equal to 0, the VGS value was completely equal to VDD, due to which all of this 1 milliamperes current was flowing through this M1 transistor. Now when I try to increase this voltage, what I'm trying to do is that I'm trying to reduce the VGS value of my M1, due to which the current through the M1 has to drop. Okay, so say for example currently right now based on the current value of Vn, I have only 0.9 milliamperes flowing through this M1. But my tail current source is expecting 1 milliampere. So where do I get the remaining 0.1 milliampere from? From my M2 transistor. Okay, it's obvious. Okay, so in a sense the current as through my M1 has got dropped, which means that the current through my M2 has to rise. Clear? Now there is a particular value of Vn at which both these currents will become half the value of each other. Okay, so at a particular point both my ID1 and ID2 will be equal, and that is this particular spot. And after then what happens is that as I increase the value of this Vn, I ultimately reach a particular value here at which my M1 would turns off. What is that input value? VDD minus VDH, right? So the moment I reach here to a value which is equal to VDD minus of VDH1, then my transistor M1 will be cut off and no current would flow through this M1, but all of the current has to flow through my M2. Okay, so the total current right now through this M2 would be equal to IS. Now, the behavior is almost clear. Now let us try to plot the Vout, because the beauty of this circuit can be revealed only when I talk about the Vout swing that I have. Okay? So what happens when the value of Vin is equal to 0? At this particular point, what I would get? VDD. Why? Because the Vout potential could be defined as VDD minus, which ID? ID2 RD. Now, under this condition, the ID2 value is basically equal to 0. When the value of Vin is between 0 to Vin1, there is no current through ID2, due to which I will have VDD. Now, after this, what happens? The current through this ID2 starts rising, which means that this quantity keeps rising, due to which the output steps down. Clear? So it is stepping down, and when I reach a particular value of Vin, which is equal to this quantity, which is VDD minus VDH1, what happens to my M1 transistor? No, M1 cut off, and because of that, my current that is flowing through this M2 is completely equal to IS itself. Now, what is the value that I would get? It's a constant, and that value is nothing but VDD minus IS RD. So the current value under this input condition is basically equal to ID2 is equal to IS. So that's the reason why I replaced here. Okay, so now let me split this entire region into 3 segments. Okay, so let me have the first region, second, and the third region. Now, when I'm in this region, let us talk about the transistors of M1 and M2 region of operations. Okay, now when I'm in this first segment, which region is my M1 is? Are you sure? Saturation. Okay. So my M1 is in saturation. What about my? Okay. So if at all, if I don't want any current to flow across this M2 transistor, the VGS value of this M2 is supposed to be equal to VDH. Okay. So that is a concept. So I have this M2, which is cut off right now. Clear? Now, in this particular region, what are the conditions that I have? It becomes difficult, right? Because I don't know what is my source potential. Without that, it becomes pretty difficult for us to really say anything about my M1 transistor situation. But still, we can think about it. How will I read this potential? The node X potential? When there is no current, what is the value that I would get out of this node Vx? I have a fixed potential Vb, and no current has to flow means the VGS of this device has to be equal to Vt. So, how will I read this voltage in terms of Vb? Vb minus Vdh. Okay. So, due to which it purely depends on the value of Vb that I have chosen. Okay. Now, from the value of Vb, I have dropped down a value of Vdh, and that is supposed to ensure that my transistor M1 is in which region? Saturation. It can be saturation, but it purely depends on the value of Vb. Am I confusing you people? So I have to write it. For a PMOS device, if I want to be in saturation regime, I have to make sure that something like this, right? Yeah. Have I really satisfied this condition under this region, such that I can say that my transistor M1 is in saturation? Think. In this segment, what is my VGS2 value? VDD, which is the highest potential that I have in my system. Okay. So, and the value of VD currently right now is it depends on the definition, which is defined as VB minus VDH. So even if I choose the value of VB to be equal to VDD by 2, still this node potential is smaller than the value of VDD minus VDH. Okay. Yeah. So I think I guess I'm right. Yeah. So let us move on to this region. Huh? Until VB equals to? Okay, I think I guess I'm making you people to confuse. Okay, let us quickly complete this. So in this particular segment, what is my transistor M1 and M2 operated in? Saturation regime. Okay, so M1 and M2 are in saturation regime, and over here, so M1 is in saturation. Okay, so M1 has something else, right? So M1 cannot be in saturation. Okay, M1 is off, and M2? So what is happening to my ID2? ID2 is, okay. So we are not pretty much clear about this regions over here. But the only thing is that, how will I read my VO max and VO minimum out of the circuit? What is the condition I have to use in order to read my VO max and VO minimum? Yeah, in that particular region, for the range of value of V out, I have to make sure that both my M1 and M2 are in saturation region, right? So it is only in this particular zone I have both my M1 and M2 in the saturation region. Now, when I move out of these zones, is the values are stuck to a particular value or it is changing further? Stuck. Why this phenomena happens? Why does this phenomena happens? You see, when we dealt with the previous circuit, like CS amplifier, we never had this situation. I have a residual load, and for this, when I try to draw V out versus V in, okay. So in this case, my M1 was in cutoff, and after then we got into saturation, and then I got into linear. But in the linear region, it was not stuck to a particular value. It was changing. Okay. Whereas in this case, you see, when I move out of the saturation regime, these values are fixed. There is no change in the outputs. New phenomena from where it came from, this new phenomena. This beautiful phenomena happens just because I added a current source, tail current source. Now, if that wasn't there, then when I move out of the saturation regime, there will be changes at the outputs. But just because I added a tail current source, it has made sure that my outputs are being stuck to a single value when I move out of my saturation regime.